The diamond you won in a previous enigma is nowhere to be found. You go in search of it, and the clues you unearth lead you to Monty Hall.
I'm the one who stole your diamond. To get it back, you'll need to guess where it's hidden.
Kettu has hidden your diamond inside one of the 3 safes in front of you. He asks you to choose a safe. Then opens one of the remaining 2, showing you that the diamond isn't there. Before opening the safe, you have the option of changing your mind.
Are you sure you don't want to change your mind?
If the diamond is in the safe you choose, you'll get it back. Otherwise, Kettu will keep it forever. Your challenge? Determine if there's an advantage for you to switch safes. You can pause to think about it, or listen to the answer now. Yes, it's a good idea to change safes. Although it may seem counterintuitive, this strategy gives you a greater chance of finding the diamond. Explanation. Let's consider the scenario where the first safe you chose contained the diamond. This happens 1 time out of 3. Kettu can open either one of the 2 remaining safes. If you change your mind and switch safes, you'll come up empty-handed every time since the diamond was in the first safe. Now let's look at the case where you initially chose a safe without the diamond, which happens 2 out of 3 times. Kettu can only open 1 possible safe without revealing the diamond. This gives you an advantage. If you switch safes, you'll find the diamond every time. As such, changing safes is the right move 2 out of 3 times. To represent this enigma on a quantum computer, we'll use several quantum gates. The NOT gate transforms the state of qubits into their opposite state. The C0 gate uses 2 qubits, a control qubit and a target qubit. If the control qubit is in the 1 state, a NOT gate is applied to the target qubit. The control Hadamard gate applies a Hadamard gate on a target qubit when the control qubit state is 1. Finally, the RY gate makes a rotation of a qubit state around the y-axis with an arbitrary angle. Qubits 0, 1, and 2 represent safes 0, 1, and 2 respectively. A quantum states notation is written with a ket symbol. The qubit associated with the safe in which the diamond is located is placed in a 1 state, and the other 2 in a 0 state. To randomize the choice, we must prepare an equal superposition of states 0, 0, 1, 0, 1, 0, and 1, 0, 0. Quick reminder. On a probability histogram, qubits are noted from right to left. As the histogram shows the different possible states once measured, the states are classical and are not written using kets. Here's an approach to achieve an equal superposition of the 3 states using 5 quantum gates. Apply an RY gate on qubit 0 with the following angle. If we measured the qubit states, we would have 2 out of 3 chances of obtaining 1 for Q0, and 1 chance out of 3 of obtaining 0. Add a control Hadamard gate between Q0 and Q1. Insert 2 C0 gates, the first one between Q1 and Q2, and the second one between Q0 and Q1. Finally, add an X gate on qubit 0. That's all there is to it. The diamond has now been hidden randomly in one of the 3 safes. The 3 qubits are entangled together, and only one of them would have a value of 1 if measured. To keep things simple, we'll assume that you initially chose safe number 2. We'll use a new qubit, Q3, to represent which safe will be opened by Kettu. Kettu opens safe 0 if qubit 3 is in a 0 state, and safe 1 if qubit 3 is in a 1 state. If the diamond was inside safe 0, Kettu would have no choice but to open safe 1. As such, we apply a C0 gate between qubits 0 and 3 to place Q3 in a 1 state. If the diamond was in safe 1, Kettu would open safe 0. Since qubit 3 is already in a 0 state at the beginning, no action is required. Finally, if the diamond was in safe 2, Kettu could open either safe 0 or 1. To make this choice random, we'll place qubit 3 in a superposition of 0 and 1 states only if qubit 2 is in a 1 state. We therefore apply a control Hadamard gate between Q2 and Q3. Note that all scenarios coexist in parallel in the quantum computer. The diamond's location is only determined once the system's measure is taken. The qubit on the left indicates which safe Kettu has opened, while the 3 qubits on the right indicate which safe the diamond is in. Here are the measurement probabilities for each scenario. Notice that the diamond is in safe 0 a third of the time, in safe 1 a third of the time, and in safe 2 also a third of the time. Kettu opens safe 0 half of the time, and safe 1 the other half. To simplify the rest of the explanation, let's switch the 2 columns in the center. Kettu opens safe 0 while the diamond is inside safe 1, 1 time out of 3, and while it is inside safe 2, 1 time out of 6. Kettu opens safe 1 while the diamond is in safe 0, 1 time out of 3, and while it is in safe 2, 1 in 6 times. In the end, you have a 1 in 3 chance of finding your diamond if you stick with safe 2, and a 2 in 3 chance of finding it if you switch to another safe.